Hello friends, Mr. Burrell here. We're in the middle of Unit 4, talking about similarity. We just finished talking about dilations, meaning expanding or reducing, enlarging or reducing images and how that works and what it looks like and how we do it. We're going to kind of extend that now and we're going to talk about ratios and similar triangles. So on the concept of similarity, we're going to talk about what similar triangles are, how we recognize that triangles are similar, what that means, and we're going to review what ratios are a little bit. So, by the end of this lesson, these are the things that I hope you're able to know. I want you to be able to know the angle, that's what this double A stands for, similarity theorem, and use it to prove two triangles are similar. I want you to know the side, that's what the triple S stands for there, triangle similarity theorem, and use it. And know the side, triangle similarity theorem. That's what this SAS stands for. And use it to prove triangles are similar. So before we get to those similarity theorems, first of all, I have a problem here. I have 3 over x equals 6 over 12. How do I solve this? What do I do in order to solve this? Well, the way that I would go about solving this, and hopefully this terminology sounds relatively familiar to you, I would go ahead and cross multiply. If I have two fractions that are equal to each other, I can cross multiply. 3 times 12 is 36, and then equals x times 6 is 6x. That looks a lot friendlier to solve, right? Then I would just divide by 6 on both sides, and I'd get x equals 6. That would be my final answer, x equals 6. So, on that note, let me erase some of this stuff. I'll put my answer off to the side here, x equals 6. We'll be using ratios a little bit later when talking about similar triangles. We're going to talk about ratios, so I want to make sure you're familiar with what that means. When I say a ratio, I'm talking about the relation between two numbers. So like the ratio of 1 to 2, sometimes you see ratios written this way. So if I had in a classroom, I had one student for every 2 desks, that would be a ratio of 1 student to every 2 desks. That's what a ratio is. It's a comparison between two different quantities. Sometimes ratios are written like this with this colon in the middle. Sometimes they're written as like a fraction, 1 over 2, or sometimes they're written like this, like 1 to 2, a ratio of 1 student to 2 desks, you know. So a ratio is the comparison between the relationship between two different quantities, often written as a fraction. With what we're going to be doing today, that's what we're going to see the most often, a ratio or a fraction relating to different quantities. So, that's what a ratio is. This lesson we're going to be talking about similar triangles. What does the word similar mean? Think about that for a minute. What does the word similar mean? Just in the traditional English word sense. What does similar mean? Well, some of the things that come to my mind, if two things are similar, they're not exactly the same, right? They're not exactly the same, but they're close. They're not exactly the same, but they're close. They're similar. That's what I think of when I think of the word similar. So in math, when I'm talking about geometry, when I'm talking about similarity, objects are similar if they have the exact same shape. So they have the exact same shape, but they may be dilated, meaning they may be enlarged or reduced. But the ratio of corresponding sides must be equal. So say I had this little triangle right here, and this big triangle right here. Say this was an equilateral triangle, meaning all the sides are the same and all the angles are the same. This would also be an equilateral triangle, meaning all the angles are the same and all the sides are the same. So they're not the exact same size, but they are the same general shape. They're both equilateral triangles. One is just bigger. Notice that all the angles stay the same in this triangle, and the sides get bigger, but the sides get bigger by the same factor. They get bigger by the same scale factor with what we talked about with dilations, or the ratio between their two sides are going to be the same. So most of what we discuss when we focus, we'll focus on triangles, and we say that two triangles are similar if their corresponding angles are congruent, like these equilateral triangles, and the ratios of their corresponding sides are equal. So if I said the length of the side of this triangle is 2 and the length of this side of this triangle is 6, the ratio or the fraction of these sides would all have to be the same. And we're going to see that here in just a minute. And just to relate to what you've already learned about, in Math 1 you talked about congruent triangles. So you talked about congruent triangle theorems. So the difference here when we're talking about similarity triangle theorems is we're not talking about two triangles that are exactly the same size or congruent. We're talking about triangles that are similar. So the ratios of their sides are going to be the same. We'll talk about a little bit more what that means. So just in general, in the real world, when I talk about similar figures have the same shape, again, but not necessarily the same size. So I have like these little mini statues of liberty. They're all statues of liberty, but they're different sizes, right? I have like the little toy Eiffel Tower with the big Eiffel Tower, a little Hot Wheels car, a baby giraffe, and a big giraffe. So those are all examples of similar figures. Let me move my face so you can see the head of the big giraffe there. This symbol right here, this little squiggly here, is the symbol we're going to use to relate two similar objects, to write that two objects are similar. So, there are three theorems we're going to discuss that prove two triangles are similar. The angle-angle theorem, the side-side-side theorem, and the side-angle-side theorem. So those are each of the theorems that we'll be discussing in this video. Okay, so the first theorem for proving two triangles are similar is the angle-angle similarity theorem, which states if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. So this is in your guided notes. If two angles of one triangle are congruent to two corresponding angles of another triangle, then those triangles are similar. So let's take a look at this. Traditionally, I'd have you do this in a group, but on this page in your guided notes, we're going to go ahead and fill out together. So I have two triangles here, QRS and CDE. Here, these two triangles. So we're going to go ahead and take a quick look at some of the properties of these two different triangles. So for example, in QRS, measure of angle Q, and I write the triangle QRS because those are the points on the outside of the triangle. So the measure of angle Q is 78 degrees. The measure of angle R is 47 degrees. It doesn't tell me what the measure of angle S is, but something that we know about triangles is that all the angles inside of a triangle add up to 180 degrees. So, well, 78 plus 47 is 125 degrees. So the angle that's left has to be 180 minus 125 degrees. Let me just type that in my handy-dandy calculator, which gives me 55 degrees. So the measure of angle S is 55 degrees. Okay, that's something I know about triangles, is the angles all add up to 180 degrees. Let's take a look at triangle CDE. Angle C is 78 degrees. Angle D is 47 degrees. Measure of angle E is going to be 55 degrees. And let me go ahead and write down each of the sides of this triangle. So side RS, or this side over here, is going to be 16. RQ is going to be 15, and QS is 14. DE is 6.4, DC is 6, and CE is 5.6. So you notice, in these two triangles, all the corresponding angles are the same, but the sides are not. So I'm just going to quickly double check. One of my definitions of similar triangles that I mentioned earlier is that the ratio of the fraction of these corresponding sides all have to be the same. So what I'm going to do is I'm going to take the fraction of the corresponding sides, or in other words, I'm going to compare the largest sides. So RS divided by DE, or 16 divided by 6.4. I'm going to compare the smallest sides, or 14 divided by 5.6, QS divided by CE. And then the remaining side, this like middle side, 15 divided by 6. So I'm going to type those each in here and write what the decimal is. So this one is 2.5, 14 divided by 5.6 is 2.5, and 15 divided by 6 is 2.5. So take a look here. All the angles are the same. All the corresponding angles are the same. And the ratio, or the fraction of each of those corresponding sides, is also the same. So what does that mean? What does that tell us? Well, it tells me that these two triangles are similar. They're not congruent, they're not the exact same size, but they are similar. I could enlarge this triangle by a scale factor of 2.5, and it would be exactly the same size as this triangle. So down here, my similarity statement, the way that in math I'm going to write that these two triangles are similar, I'm going to say triangle CDE is similar to, this little squiggly sign, triangle QRE. And notice I wrote C and Q first because C and Q have the same angle, D and R next because D and R have the same angle, etc., etc. So that first similarity theorem, as long as I knew, I didn't even need to know all this other information. If I knew only this information, those two angles, I would be able to know that those two triangles are similar by the angle-angle similarity theorem. Okay. So the next similarity theorem we're going to talk about is the side-side-side similarity theorem. So if the three sides of one triangle are proportional to the three corresponding sides of another triangle, then the triangles are similar. So this is another theorem, another triangle similarity theorem we can use to show that two triangles are similar. Notice that on this one we know all three side lengths. I don't know any angle measures, but that's okay. If I know all the sides and the ratio of all the sides are equal to each other, I don't need to know the angles. So let me show you here. Let me move my face out of the way again. So let's check here. I don't know any of the angles here, right? But I do know, and well, I'll come to that in just a minute. Okay, so in triangle KLM, KL, so this longest side is 20. ML, this middle side is 15, and MK is 10. QR is 24. PQ is 18, and PR is 12. Okay, so if I were to go in order here, so like if I went KLM, I'd go along the longest side, the middle side, and then the shorter side in that order, you know. And if I went from R, let's see, RQ or RQP, if I went in that order, see that? In that specific order, then R and K, so measure of angle K is equal to the measure of R. I don't know what those angles are, but they will be the same. The measure of angle M is equal to the measure of angle P, and the measure of angle L is equal to the measure of angle Q. Okay, so you can kind of see what's going on there. So the side-side-side similarity theorem says that the ratio of all of these corresponding sides would have to be the same. Or in other words, I'm going to divide my largest sides, so 20 divided by 24. I'm going to compare my smallest sides, or 10 divided by 12. And then I'm going to compare my middle sides, or 15 divided by 18. So let me see what those are. 20 divided by 24 is 0.833. 10 divided by 12 is 0.833. 15 divided by 18 is 0.833. So I knew three of the sides. The ratios of those corresponding sides, or the fractions, are all equal to each other. So that's enough to say, hey, these two triangles are similar with a scale factor of 0.833. So how would I write this similarity statement? So I would write the triangle KML, so going in, or KLM, should I go that way? KLM is similar to triangle, if I'm looking at the one between the smallest and the largest sides, the one between the smallest and the largest sides, would be similar to RQP, triangle RQP. KLM is similar to RQP. These corresponding angles I line up in the same order there. So I say those triangles are similar. Okay. The last triangle similarity theorem is the side-angle-side theorem. So if two sides of one triangle are proportional to two corresponding sides of another triangle, and they're included, this is the included angles, are congruent, then the triangles are similar. So this is basically saying if I have two triangles, and all I know is that these sides are, the ratio of those sides are the same, or they are proportional, and the angle in between them is congruent, That's enough to say that the triangles are similar. Okay, so let me show you an example. Let's look at this example right here. Okay, so I have triangle ABC and XYZ here, okay? So triangle ABC, let's take a look at that. So side BC is 36 units long, AB is 15 units long, YZ is 24 units long, and XZ is, or is this XZ? Yep, is 10 units long. So I know, that's all I know about the sides. What do I know about the angles? The measure of angle B, well, that's a right angle. That's a 90-degree angle. And the measure of angle Z is also a 90-degree angle. So I have two sides on each of these triangles with an angle in between. So that gives me an idea that I'm going to be using the side angle side similarity theorem. Okay. If these are going to be similar, I already know the angles are the same, so that's good, but I need to check that the fractions of these corresponding sides is also the same. So let me compare the smallest sides and the largest sides. So the smallest sides were AB and XZ here. So let me do 15 divided by 10, and then the largest sides were 36 and 24, so 36 over 24. So 15 divided by 10, that's 1.5. 36 divided by 24 is also 1.5. Since those ratios are the same, these two triangles are similar by side, angle, side. Okay? So my similarity statement would look something like this. Triangle ABC, and I go along the shortest side to the right angle and then to the longest side, ABC. So if I'm going along the shortest side to the right angle to the longest side, that's going to be similar to triangle XZY. So it seems kind of out of order there, but notice I'm just following the corresponding sides. Short side, long side, short side, long side, ABC, XZY. So those two triangles are similar by the side angle side similarity theorem. Okay, so this next page in your guided notes, let me move my face maybe right here in the middle. So this says, determine if the triangles are similar. If yes, state which theorem you can use to prove it, and write a similarity statement. So this is what a good chunk of your homework is going to be. Now I'm going to give you a couple of triangles, and I'm going to say, are these two triangles similar? And you have to prove it to me. So say this triangle right here, for example. These sets of triangles right here. What do I know about these triangles? Well, I know that angle A is congruent to angle Y. And I know angle B is congruent to angle Z. Well, my angle-angle similarity theorem says that if I know two corresponding angles in two triangles are congruent, then they're similar. So, these two triangles are similar. They are similar by the angle-angle theorem. So that's the similarity theorem I can use to show they're similar. And my similarity statement, say if I write triangle ABC, ABC, so from this double angle to the single angle to the missing angle. If I go from the double angle to the single angle to the missing angle, that's going to be similar to triangle YZX. See that? So those two triangles are similar by the angle-angle theorem. Let's check this one. So I know two angles. This one's 81 degrees and this one's 81 degrees. But this one's 60 and this one's 40. Okay, well, right now it doesn't seem like they're similar, but I'm going to have to double check what these missing angles right here are. So for example, if I wanted to find this missing angle in this triangle, I'd have to take 180 degrees minus 81 minus 60. 180 minus 81 minus 60 is 39 degrees. So this angle is 39 degrees. But if these triangles were to be similar, both of these would need to be the same. And they're not. So, these are not similar. They're not, so that's all I have to do. They're not similar, I just showed it. There's not two corresponding angles that are congruent, so they're not similar. Let me move this up here. So, on these triangles, let me look at these ones right here. These ones I'm not going to write a similarity statement because there's no letters on them. But I know two sides on this triangle and an angle in between. So if I'm to prove these are similar, I'm going to use the side angle side similarity theorem, which means the angle in between them would have to be congruent, which they are, and the ratio of the corresponding sides would have to be the same. So I'm going to divide my smallest sides, 3 divided by 6, and divide my smallest sides, or my biggest sides, 4 divided by 8. In both of those cases, 3 divided by 6 is 0.5, 4 divided by 8 is 0.5. They're the same. So yes, they are similar by the side angle side similarity theorem. These were similar by angle angle. These were similar by side angle side. Let's check this last one. So this one, I don't know any of the angles. I just know the sides, which is fine. These are going to be similar only if their corresponding sides, the ratios, are the same. So I'm going to go ahead and divide my longest sides. So let's say 20 divided by 25. Then I'm going to divide my smallest sides, 16 divided by 20. 16 divided by 20. Then I'm going to divide my middle sides, 18 divided by 22. Let's see what those give me. 20 divided by 25 is 0.8. 16 divided by 20 is 0.8. 18 divided by 22 is 0.81818. So look, those are close, but if these were similar, all of these numbers would have to be exactly the same, and this one is not. So are these two triangles similar? No, they're not. So I'm going to skip this part, but that's it. That is the end of this lesson. Hopefully by the end of this lesson, these are the things you know. I want you to be able to know the angle, side, side, and side, angle, side similarity theorems, and be able to use those theorems to prove whether or not triangles are similar. So I hope that was helpful. Please don't hesitate to reach out to me if you have any questions whatsoever. Please let me know. And I hope that you enjoyed that video as much as I did.